Hello, this is Dr. Strickland. In this video, we will investigate the intramolecular version of the Claisen and aldol reactions. Take a minute to read through these student learning objectives. These are the things you should be able to do by the end of this video so that you're ready for the more difficult things we will do together in class. Now, Claisen condensations always involve either two esters or an ester and something else like a ketone or a carbonate. And we find that a 1,6 diester will form a 5-membered ring beta ketoester, and a 1,7 diester will form a 6-membered ring beta ketoester. So let's look at the numbers and at the functional groups. So if I go from carbonyl to carbonyl, it's 1, 2, 3, 4, 5, 6, 7. So that's the 1,7 diester. Now, the reason it forms a 6-membered ring is that we're not forming a bond between two electrophiles. It has to be between a nucleophile and an electrophile. So if I make an enolate ion right here, alpha to one of these esters, then it's going to attack the electrophile on the other end of the molecule, which is here, and that's 1, 2, 3, 4, 5, 6. So let's see what happens, and then we'll come back and put the product in there. So we got a couple of steps, and remember that the alkoxide in step 1 has to match this piece right here so that you don't get transesterification. All right, so I'm going to redraw my molecule here. Got an ester on one end and an ester on the other end. 1, 2, 3, 4, 5, 6, 7. And I'm going to draw in these two hydrogens that are alpha to the ester on the right because I'm going to remove one of them. I have an alkoxide. In this case, it's methoxide. Probably was put into the reaction as sodium methoxide. And so deprotonation here puts the electrons up onto this carbon, and there are different resonance contributors, but you don't have to draw all the resonance contributors when you're doing, the products of a reaction. All right, so this end is still just the way you left it. 2, 3, 4, 5, 6, 7. All right. We've removed one of the hydrogens here, left its electrons behind. Now this is the nucleophilic atom, and this is the electrophilic atom right here. And so we have the nucleophilic attack of this nucleophilic atom on the electrophilic atom. The electrons go up onto the oxygen. So let's see, let's put in some annotations here. All right, so this is going to make a 6-membered ring. All right, and then the question is, well, what went where? So I think it's a good idea to just choose a couple of atoms. These are the two that are going to be my atoms that formed the new bond, and there is the new bond that formed. Okay, at this one, what we've got is an alkoxide and a methoxide. Make sense? Like that. And then this one is still attached to that other ester. All right, so what happens now is that we're going to reform the carbon-oxygen double bond and kick out the alkoxide, because this is a very basic environment. Just this is the conjugate base of methanol. It's a pretty good base, so it's fine to kick out a methoxide. So what it's going to make is this, and we've got a ketone functional group there. We've got the ester in the beta position. And then we've got this methoxide. But since this place right here between those two carbonyls is pretty acidic, we can do an acid-base reaction, and we at least need to check and see whether the equilibrium would prefer the products of this acid-base reaction. All right, so that would give us the anion right here and methanol. All right, and so we can check the pKa's because that's how you check to see which side of an acid-base equilibrium is preferred. And so the pKa here is about 10, and the pKa here is about 15. So it's going to prefer this side, which means that this looks like it should be the product, but it's not. In fact, you have to have aqueous acid added in order to make the final product, final uncharged product. So I've got this guy. With the anion right there in the middle. And hydronium ions. All right, and that will protonate it, and that's how you get to the final product. Remember that clasins actually won't go unless the alpha carbon that's being deprotonated has two hydrogens that it can give. Okay, and so this is a beta keto ester because the ketone is in the beta position relative to the ester. You look at this carbonyl carbon, and then that's the alpha position and the beta position. This is a beta keto ester. All right. So let's see. Hold on, before we leave, we should probably just put the product up here. All right. There. All right, so come on down here. Let's do an intramolecular aldol. Now with aldol additions, remember you're going to have either ketones or aldehydes or one of each. So we're usually going to deal with symmetrical molecules when we do intramolecular reactions. So this is a symmetrical ketone. So a 1,4 diketone or a 1,6 diketone will form a 5-membered ring, and the product will be a beta hydroxyketone. If you have a 1,5 diketone or a 1,7 diketone, it'll form a 6-membered ring, same kind of functional groups. All right, so remember that you're going to have to remove an alpha hydrogen to make an enolate ion and then attack the other carbonyl. So if we made the enolate ion here and then attack that carbonyl, it would just be a 3-membered ring. But if we made it here and attacked there, it would be a 1, 2, 3, 4, 5-membered ring. So that's what we're going to do. So we're going to form the enolate there and do the nucleophilic attack at that electrophilic atom. And so let's follow the mechanism, see what happens. All right, so we'll just set up our starting compound. And I'm going to just enlarge, well, I'm going to draw in the carbon and the hydrogens so that we can do our deprotonation. We're going to use hydroxide instead of alkoxide, because this is aqueous base. We're going to form the enolate ion on that carbon. And now we're ready to do the nucleophilic attack. All right, there's the nucleophile. Here's the electrophile. Nucleophile has to have a pair of electrons that it can use to form the new bond. And so we end up with 1, 2, 3, 4, a 5-membered ring. All right, and so let's place everything. Let's say if this was the nucleophilic carbon, this was the electrophilic carbon, this was the new bond that formed. Okay, so what went where? Let's see. At this carbon, we've got the alkoxide and a methyl group. And then with this guy here, we've actually got that carbonyl, that ketone, alpha to it, like that. Okay. And so then a protonation is all we need to do to finish this one up. Since it's aqueous base, the proton donor will be water. Proton acceptor, of course, was the hydroxide. Sorry, going the wrong way. Here, and then to here. Let's just make some more hydroxide. All right, so there's the methyl group. There's the hydroxy group. There's ketone. And this is a beta hydroxy ketone relative to this carbon. This is alpha, this is beta, so it's beta hydroxy ketone. All right, so let's just transfer the product up into this box here. And you can color code it however you like to remind yourself of where the pieces went. All right, so this was a deprotonation, a nucleophilic attack, and a protonation. Let's see if we did all of the annotations up here. Oh, no, we didn't. Okay, so, and all of these steps should be equilibrium. So let's put those double arrows in there. Okay. And there. So we had a deprotonation, a nucleophilic attack, an elimination, an acid-base reaction, and the second step, just a protonation. All right. So this is the basic story on the intramolecular version of the Claisen condensation and the aldol addition. If you have any questions, please send them to me.